Okay, so in this video I'm going to start talking about curve length and surfaces of revolution and volumes of revolution and things like that. And so I just want to sort of back up and sort of remind you what a derivative is. So I have made this curve here in my little graphing program, y equals x cubed minus 4x. And here it is. And so what the derivative wants to do is the derivative wants to find the slope at, well, it wants to find a slope at all points. But suppose I want to find this slope at this point right there. Okay? So what I want to do is right now that's curved. So what I want to do is I want to zoom in until basically it looks straight. And so I zoom in until it looks straight, and then basically I can find x and f of x, and then I can do x plus h and f of x plus h, and then I can sort of do calculus to figure out the slope of that point. So I'm going to switch over to pencil and paper and show you what we're doing with that. Okay, so then as we just showed on my graphing program, I have a curve that looks like that, roughly, and I wanted to find the area there, or I wanted to find the slope there, and so again, what we're going to do is we're going to basically approximate it as a little triangle like that. And so we're going to say that this is going to be my dx, and this is going to be my dy, and then so my slope is going to be then the slope of that line is going to be dy over dx. And so again, sort of, I'm going to just, rather than trying to write small, I'm going to get a new sheet of paper and I'm going to zoom out. And so basically I've got some curve coming in like that, and I've got, this is the point x, f of x, and this is the point x plus h, f of x plus h. And so my slope, m, otherwise known as dy dx, is going to be f of x plus h minus f of x over x plus h minus x. And so I want to take the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, and then we learn all these tricks on how to do that with specific functions. So the function that I had before was x cubed minus 4x. And so then we just sort of learn our little rules, which we've learned. And I find that the derivative of that is 3x squared minus 4. Okay, that's all good. Now, what I want to do next is I want to find curve length. Okay, so looking at curve length, we come up with that same concept where we're going to take that, we're going to blow it up. So we've got a curve coming in like that. And I make an approximately right triangle. And the smaller I make that, the better, the closer to being a right triangle it's going to be. And so I said that's going to be dy. And this is going to be dx. Well, that means that this side of, that means that the hypotenuse is going to be approximately the square root of dy squared plus dx squared. So a, b, c. Pythagorean theorem is a squared plus b squared equals c squared. So we have an approximately right triangle. A squared plus b squared equals c squared. So a is dy, b is dx. So that means that dy squared plus dx squared equals c squared. So it means that the hypotenuse is going to be dy squared plus dx squared, square root of that. Okay. So now what I want to do is I'm going to write this as square root of dy squared over dx squared plus dx squared over dx squared times a dx that's outside of the square root sign. So what I did is I basically, well, I'll let you figure out the algebra on that. I'm not going to try to explain it to you. So then this becomes dy dx squared plus 1 dx. Okay, so this little piece of this little triangle has a length which is the derivative of the function squared plus 1, take the square root of that, multiply it by dx. Okay, so then that gives me my curve length formula. Is what I'm going to do is, this means add up all of the okay, rather than trying to write it all out, let's go from A to B. What this integral is telling me to do is take a function, find the derivative of the function, square it, add 1 to it, take the square root of that, and that's going to give you the length of all of these little hypotenuses. Now keep in mind that this is sort of a blown up thing. So I've divided my function into a whole series of little right triangles. And this function here gives me the length of each one of those. Now, the integral is telling us, the integral is basically an infinite summation. So I'm taking an infinitely small, I'm taking an infinitely large number of an infinitely small number of these. I'm sorry, let me say that again. An infinitely large number of infinitely small hypotenuses, which are given by that function. And then I'm adding them all up from one limit to another limit, and that's going to give me the entire curve length. So if I've got y equals x cubed minus 4x, I find dy dx is equal to 3x squared minus 4. And then I find that dy dx squared is going to be equal to, well, I'll do it out. So foiling it out, I'm going to get 9x to the 4th minus 24x squared plus 16. Then I want to add 1 to that. So then I'm going to get the integral of square root of 9x to the 4th minus 24x squared plus 17 dx, and let's find it from -2 to 2. That's what I want to do. Now, how do I find that integral? Well, the way that I find that integral is that I use numerical integration. And so let me switch back over to the computer to make that happen. Okay, so here I am looking back at this, and so now what I want to do is you can go online. There's a lot, by this point in time, hopefully you know how to do numerical integration. And so what I'm going to do is I'm going to find the integral from 2 to -2, and I want to go square root, I'll just do it this way, 9x to the 4th minus 24x squared plus 17 to the 0.5. And so there I find out that the length of the curve from here all the way through to here is going to be 13.2683. So that's how I find curve length. Is the first thing I do is I find the derivative of this function, and then I square that derivative, I add 1 to it, I take the square root of it, and then I integrate it from my two limits, from whatever my low point is to my high point. And basically, I'm going to have to do that numerically. The set of functions that you can do it analytically is extremely small, so I'm basically just going to have to do it numerically. Okay, so then the next video what we're going to do is we're going to start looking at surface of revolution.